This next section links back to some extent with parametric differentiation that we did right at the very beginning. It also has strong connections with chain rule, and depending on the complexity of the question, you may also need to invoke some of the other rules that you've come across during this chapter. The main crux of this is chain rule. So we're using the idea that we can chain together derivatives in different variables, as many as we like really. In some cases, they'll have you chain together more than two, to connect the rate of change with the thing we're interested in by using rates of change for various other variables. I'd like you to start by trying these four questions. Read carefully so that you know if you're looking at dx by dt or a dt by dx, because it changes. I've tried to make a few little changes within each question that you do. So read carefully and see if you can come up with an expression for dy by dx just using the chain rule idea, maybe a little bit of basic differentiation in a couple of cases, and multiplying terms in the appropriate way. When you're done, unpause the video and we'll go through some answers. So for this first one, all we need to do is take the two terms we've been given and multiply them together. We've got dy by dt and we've got dt by dx. So if we were to multiply dy by dt and dt by dx directly, then the t's cancel from the top of one, the bottom of the other one, and that gives us exactly what we're looking for, which is dy by dx. Now the next one is similar but not quite the same. Instead of dt by dx, we've got dx by dt. In fact, this is more likely to be the kind of thing you'll end up with. Getting dt by dx in terms of t seems like an unlikely sort of thing to get. But dx by dt, well, that's the kind of thing that you've had when you did parametric differentiation, if you recall. So in order to find the derivative for this, we're going to need to flip over that dx by dt to turn it into what we need. We still want the same kind of situations we had above, where the dt's will cancel out and you get dy on the top and dx on the bottom. Probably the neatest way of writing this is 1.5 cot t rather than 3/2 tan t, but that's perfectly valid if that's what you've written. For the next one, there's a little more work to do. I've still given you dy by dt at the beginning, but you've just got x on its own here. And in order to find dy by dx, you're going to need to combine dy by dt with dt by dx. In order to do that, you're going to need to find dt by dx. In order to do that, you're going to need to find dx by dt. So start by differentiating with respect to t, and you'll get 15t squared. So dx by dt is 15t squared. That means dt by dx must be the reciprocal 1/15t squared. And that's where this piece comes from. Put it all together, we get 2ln t over 15t squared. Now the last one may have had you stumped. Even if you've got the right answer, you may not be convinced that you have. I've thrown all sorts of weird things into this one. Firstly, it's dy by dr instead of dy by dt. Then we've got dt by dr, some kind of link between t and r, whatever r is. And then finally, we've got x in terms of t. So how are we going to connect these? We need y related to x, dy by dx, the rate at which y changes with respect to x. But all we have involving y is dy by dr. So we're going to have to use that one. That's the only connection we have to y. How do we build the chain from there? Well, do we have anything involving r? Yes, we've got dt by dr, but we'd like something that links us to x. Well, we have x, but we have x in terms of t. So we're going to need to find something that links x and t. A derivative linking x and t would be dx by dt or dt by dx. And that's what we're going with here. We're going to find a way to link them so that the dr's cancel with the first two terms and the dt's cancel with the second two terms. And overall, you'll end up with dy on the top, dx on the bottom. We'll need to use the reciprocal of dt by dr, just like we did in the second question. And we're going to use the reciprocal of the x by dt over here. X was e to the 3t, so dx by dt will be 3e to the 3t. And then to get dt by dx, we do 1 over that thing. And that gives us 4/15r e to the 3t. You might be confused by it because it's got a bunch of different variables in it. We wanted dy by dx. We've ended up with something that involves r and t. That's often the case with this sort of question. You might well end up with variables, one or more in some cases, although not very often more than one. but certainly variables that don't necessarily crop up in the x and y that you might be expecting at the very beginning. Now, the best way to learn modeling with differentiation is to do a bunch of examples. There's no new theory involved here. You're not going to be shown any new abstract techniques. All we're doing is recognizing how we can apply the ideas and the knowledge we already have to questions that may not on the surface appear like anything that you know what to do with. It's often a lot trickier when you come across a question in context than it would be if you already had the notation set out for you and all you needed to do was manipulate the symbols. So let's start with this one. We have a square with side length x, which is increasing at a rate of 3 centimeters per second. At what rate does the area increase? And the way I'm going to set this out is the standard approach that I use for problem solving. It's often really helpful, especially if you've got a problem that's a little too hard to get your head around or has a lot of different terms that you need to be very careful of. I start always by asking myself two questions. What do I know and what do I need? What I know relates to the information that's provided in the question. So this is specific to the particular scenario that's being described. What have they told me within the wording of the question that I will rely on and make use of during my answer? What do we need? That question is relating to what the requirements of the question are. What have they asked me for? So in this case, we're talking about this final bit. At what rate does the area increase? I need to know what they're asking me and I need to understand what they're asking me. So when they tell me about the side length of x, and they tell me it's increasing at a rate of 3 centimeters per second, that's information that we've been given in the question. But when they say something about the area rate of increase, that's what they're asking us for. And the third part that I'm going to try to answer for myself is what can we use? In other words, what bits of mathematical techniques or what particular mathematical ideas might be necessary for me to move from the information I have to the information I want. We'll work through these bit by bit. To start with, we define the variables. It's a good idea to do this explicitly within a question, especially if there's lots of things going on. The more mistakes, the more you leave out steps like this, the more likely you are to make little mistakes. I've done it myself even while preparing this. If I don't write down what the variables are, I'm likely to make a little mistake, even if it's just with the units being wrong. So if you write down explicitly what each variable represents as you go through, you'll find you have fewer problems. Now we've got x that was given in the question, but it asks about the area, so it makes sense to also define a variable to be the area. We'll use capital A, that's going to be the area of the square, and that will of course be in square centimeters if x is in centimeters. That'll make life a bit simpler. We've also got t. That's another thing which is not directly mentioned in the question, but it's something we're going to need. If they're talking about the rate at which the side length increases, and they're asking about the rate at which the area increases, that is a rate with respect to time. So often when you deal with a rate of increase or a rate of decrease, the rate is implicitly with respect to time. It's how often a thing happens, how many times a second, or how much you move within a second, etc., etc. This has a bit of a giveaway in the units, 3 centimeters per second. That clearly refers to a rate of increase with respect to time. Next, we interpret the information they gave us, that 3 centimeters per second, as a derivative statement. This is basically a miniature differential equation. It's an equation because it's got an equal sign, but it's not the standard sort you can just rearrange and solve in the ordinary way because it's an equation involving derivatives. That makes it a very different beast. But it's something we can use and manipulate because we've got chain rule, so we can work with that, and we're going to write it down in that form right in the very beginning. Next, we clarify exactly what we're looking for. We're asked to find the rate of change of the area, which means the rate at which capital A changes with respect to t, the time. So we're looking for dA by dt. Now this is the most important bit. We've managed to identify exactly what we know, and we've clarified what the letters represent that we're going to use, and we've identified exactly what we need to find. I've got dx by dt. I'm trying to move my way towards dA by dt, and now I can start to see a bit more clearly what I'm going to need in order to make that transfer. So if you think of it in terms of the variables we're looking at, we're trying to use the idea of chain rule not just directly, which we will do, but also the concept of building a chain. We've got a link between x and t, and we're trying to construct a link between a and t. So it kind of makes sense that a link between a and x would be useful. Not only that, but it's something that we can get because there's one bit of information in this question that I haven't used explicitly yet. It's a square. They're describing a square with side length x. And we don't just have to think of this area as a, we can think of it as x squared. So if we're trying to find the link between a and t, we can make use of the fact that we have a link between x and t provided in the question. We can connect a and x together using shape formulae. There are a bunch of shape formulae that you'll need to make sure you know for this topic, but the area of a square is hopefully not one that you have too much difficulty with. Finally, we'll combine those together in a chain. So this is where chain rule really comes in handy. We want dA by dt, the rate at which a changes with respect to time, and we can get it by combining dx by dt with dA by dx. And then, once we do that properly, the dx's will cancel out. We'll be left with just the pieces that we want, dA on the top, dt on the bottom. Let's see what that looks like when we put it all together. dx by dt is 3, that's what we're given, and the area can be represented in terms of x, the side length. Area equals x squared, so dA by dx, the rate at which the area changes, is equal to 2x. Now, if you think about it, it kind of makes sense. If the side length is increasing at a regular rate, let's say it's a 2 by 2 square at a certain point, well, if in the next second it increases by 3 centimeters, it'll now be a 5 by 5 square. It's gone from an area of 4 to an area of 25. But you give it another second, it's an 8 by 8 square, which is an area of 64. Another second, it's now an 11 by 11 square, it's 121. The area is increasing faster than just a constant rate. So it's going up at a greater and greater rate. It's a quadratic. So it makes sense. And the rate at which it increases depends upon the side length x. In other words, if it's a really big square and you add an extra 3 centimeters to each side, then the area gets a lot bigger because your 3 centimeter strip that gets added on will be a very, very long 3 centimeter strip. Now we can use that dA by dx. We can build it into the chain that we wanted. dA by dt is what we need. We're going to get it by finding a derivative with an dA on the top and finding one with a dt on the bottom. And if they don't happen to be the same one, we need to find a chain that links them together. And in this case, that chain comes from the side length x. So we have 2x for dA by dx. We have 3 provided in the question for dx by dt. And that gives dA by dt. 6x is our answer. And this first question I was deliberately vague. I wrote, at what rate does the area increase? Might be tempting to think that it's going to be a nice constant rate. We'll get a number at the end. But in fact, the rate at which the area increases depends upon the side length. A classic additional bit that you might have in a question like this is, at what rate does the area increase when the side length is 10 centimeters? In which case you find your expression and you sub in 10. And we say, oh, it looks like it's increasing at a rate of 60 centimeters squared per second when it's reached a length of 10 centimeters on a side. Another way they might phrase this is, show that the area increases at a rate proportional to the side length. And we've demonstrated that we get 6 times the side length. So when the square is twice the size, the area will be growing at twice the rate. Here's our next one. Now we've moved into 3 dimensions. A cube's volume grows at a rate of 5 centimeters cubed per second. Find an expression in terms of the side length x for the rate at which the surface area grows in centimeters squared per second. There's a whole lot of things in this one. Firstly, try to get a feel for the actual situation. We're talking about a cube which is growing, and the way it's growing is the volume is increasing by a fixed amount. The analogous situation would be blowing up a balloon. You blow a certain amount of air into the balloon, and the volume will therefore increase at a fixed rate. Whatever rate you're blowing the air into the balloon, that's how quickly the volume is increasing, probably a reasonably constant rate. But the radius of the balloon does not grow at a constant rate, and the surface area of the balloon will not stretch at a constant rate because the radius and the surface area are not following the same pattern as the volume of the balloon. You might already be imagining, if you've got a very large balloon, you could stick a whole extra litre of air into that large balloon, one of these big punch balloons 2 foot across. You put a whole extra litre in, you may not even be able to see the difference. The difference in the radius may be very small. Whereas if you've got a balloon that's only the size of a water balloon, and then you stick an extra litre of air in, it's going to grow significantly. There'll be a marked difference, probably twice the surface area already. So there are differences with the rate at which the volume grows, the surface area grows, and the length grows. That's what we're going to be seeing here as we put all these derivatives together. The first thing, like we did before, is to define our terms. That means we're going to go through and make sure we're specific about what every single letter represents, whether they're letters provided in the question or they're letters that we introduce in order to describe the situation. State the relevant formulae. This is a cube. The formulae are not going to be very complicated, but it's always a good idea to write them down. You'll need them because you'll end up differentiating so that you can construct the derivatives you need. But also importantly, sometimes the shapes are quite complicated. You want to know which formulae you need. Chances are at some point you'll need the volume of a sphere, the volume of a cone, that kind of thing. I'll put a list up in a bit. And the last thing, choose your derivatives carefully. Think about which ones you were provided with and think about which ones you are asked for, not just the variables themselves, but the derivatives that you're going to need to construct between pairs of variables, and think about the chain you're going to create to link them all together. We'll go through our questions again. What do we know? Well, looking at the question, we're told a few things. What do we need? We've got information in the question about what they're asking for, and what can we use, how we're going to get between those two things. So let's start with the volume. It tells us at the beginning the cube's volume grows at a certain rate, so we'll define the volume to be V, capital V. We'll define the surface area to be capital A. We'll define the time to be T. Time is measured in seconds in this one. We can see that from the units given in the question. And we're also going to have X, which is mentioned in the question, so I should use the same letter they've used for the length of the cube. And the last thing we're told is that the rate at which the volume changes is 5. It grows at a rate of 5. If it said it was shrinking at a rate of 5, the only difference would be negative 5. In other words, the rate at which the volume grows is negative 5 centimeters cubed per second. What do we need? The question asks us for the rate at which the surface area grows. In other words, that's dA by dt. It says in terms of the side length x, so I'm expecting this result, even though it's the rate at which area changes and it's with respect to time, we're expecting it to involve x somehow. So how do we get between them? Well, we've got a link between t and v. We need a link that takes us all the way from t to a, a connection between t and a. So do we have a link between v and a? Well, not really, not directly. There's no obvious formula for the surface area in terms of the volume or the volume in terms of the surface area. You could construct one, but you might find it simpler to use a more natural go-between. Think of this a bit like with parametrics, where there's a natural, obvious third thing that you can bring in. Volume is naturally defined in terms of the side length of the cube, and area is also naturally defined in terms of the side length. So why not consider both of them in terms of the side length and just connect the two derivatives afterwards? It'd be the same if you're having some difficulties trading your rubles into yen, but you wouldn't have any difficulty trading either of them for US dollars, then swap for US dollars and then swap from US dollars back into the one you want. It's going to be easier in this context to work within the confines of the way cubes work. If there's a natural variable that you want to be making use of, then do it. With things like spheres and cylinders, you might find it helpful to think in terms of the radius. So we need a link directly between A and T. We've already got a link between V and T, and we know that we can connect V and X and A and X using shape formulae. And then the final thing is to build the chain. This chain looks trickier. That's because we've got to incorporate X into our equation as well. But we still have the same kind of idea. We're looking to link dA and dt. We would need dA by dx to cancel with dx by dv to cancel with dv by dt. So can we construct each of those? Well, dA by dx we'd be able to get if we had a formula linking A and x, which is what we were talking about there. We can do that because we know that A is the surface area of a cube. We can get dx by dv by flipping over dv by dx, and we can get dv by dx by thinking about the formula for the volume of a cube. And the final piece, dv by dt, is exactly what was given in the question. They told us that dv by dt is actually 5. It's just a constant. That'll be a nice easy one to incorporate. So let's try it. The surface area of a cube is 6 multiplied by the area of one face, because there are 6 faces, so 6x squared, and that gives the rate of change of the area as 12x. Volume is very similar. We have volume of x cubed, giving us the rate at which the volume changes with respect to x, the side length, as 3x squared. Put them all together and take care with the dv by dx because we need to use dx by dv. So I'm using the reciprocal of 3x squared, combining it with dA by dx, which is the 12x, and finally bringing in the 5, which represents dv by dt from the question, and that gives us our result. And you can see that although it is the rate at which the area changes and it's with respect to time, that it depends upon the side length. It will change as the side length changes. So the volume is growing at a fixed rate, but the surface area will grow at a slower and slower rate the larger the cube gets. So if the cube has side length of 10 centimeters, then the surface area will grow by 2 centimeters squared every second while you're increasing the volume at this fixed rate of 5 cc's a second. But once the cube has grown to a larger size, say 20 centimeters on a side, then the area is now only increasing at a rate of 1 square centimeter a second. Once x becomes 100, the surface area is only increasing at a rate of 1/5 of a square centimeter a second, and so on. This next question involves spheres, so we need to be thinking about our volume and surface area formulae. Also, it's referring to a balloon which is being deflated in such a way that the area decreases at a constant rate. So instead of deflating or inflating a balloon with a constant flow of air in or out, we have the surface of the balloon itself, the surface area, changing at a constant rate, a certain number of square centimeters per second. The question asks us to show that the volume decreases in proportion to the radius. In other words, that dv by dt, which is the rate at which the volume changes, is equal to some constant multiplied by the radius. It's also given us some additional information in terms of the rate at which air is lost for a particular radius, and that will help us, hopefully, to find whatever unknown constant is kicking around. So let's start as we normally do, see if we can write down what we already know. And although there's quite a lot to squeeze in here, we're going to include all the variables that are being defined, the volume in cubic centimeters, the surface area in square centimeters, the radius in centimeters, which will be useful for linking things like volume and surface area, and finally the time in seconds. We're also given that dA by dt is equal to negative k. Where does that come from? Well, we were told in the question that the material decreases in area at a constant rate. In other words, the rate at which the area changes over time is negative and constant. It's a decrease and it's at a constant rate. The negative in front of the k is more convention and preference than it is absolute necessity, but it's a very useful convention, because if you look at dA by dt equals k, then yes, you know that that means a constant rate, but it's not obvious unless you've got some natural convention built in whether it's an increase or a decrease. If I put minus k, it kind of flags it up to me, so I'm already thinking of this as going down rather than going up. So anytime you see a k in differential equations, it's likely to represent a positive constant. Not always, and if we don't know if it's positive or negative, you wouldn't stick a minus sign in front. But if we know that we're thinking of a rate of decrease, or if we have exponential decay, for instance, we're more likely to have e to the minus kt than we are to have e to the kt and then set k to be a negative number. The next thing we're told is that the rate of decrease of the volume is equal to negative 30 when r is equal to 5. So we're given the value of dv by dt. And what do we need? Well, in this case, it's pretty straightforward what we've been asked for. There's quite a lot that goes into this, but we're looking for information about the rate at which the volume changes. So it says show that the volume decreases in proportion to the radius, and it asks us for an expression for dv by dt, given all of these additional things. So the rate at which air is lost for a particular radius, that's part of what we can work with. And the fact that this is a spherical balloon we're going to make use of, but what we're trying to get towards is dv by dt. And how we get between those two, this is where we start thinking about the chain that belongs in that place. We've already been given a link between we're looking for a link between V and T. We already have a link between A and T. So we need to somehow link A and V together. That would seem sensible. Well, A and V don't have a natural connection, but A connects directly to the radius, and so does V. So we can make use of that. Incidentally, the formulae for things like spheres, cylinders, cones are things you need to be familiar with. We combine them to form a chain. We have dv by dt, which is what we want, can be constructed if we can link V and R, the volume and the radius, which seems doable. If we can link R and A, which is the reciprocal of dA by dr, we should be able to do that if we can get the area in terms of the radius. And finally, dA by dt, which was provided in the question as negative K. So linking T and A, which is what we already have. We've got that connection provided for us. We can link A and R using the formulae for spheres. Similarly, we can link R and V using the formulae for spheres. And that completes a chain that goes all the way from T to V. And the dV by dt is what we're looking for at the end. Here are the formulae that you should be remembering for this topic. If you're asked a question involving cuboids, spheres, cylinders, cones, you will be expected to know these ones. You'll notice a surface area of a cone is not included. As far as I'm aware, they're not going to be mean enough to expect you to remember the surface area of a cone formula. I'll be honest, I think I'd have to re-derive it for myself. It's a little bit of a messy one. But basic results about cones, like the fact that it takes up a third of the volume of the cylinder that it sits inside, or that the radius and the perpendicular height and the slant length can be connected using Pythagoras, which if you draw yourself a neat enough diagram, hopefully you notice, and you better make use of that. Depending on the format of the question, you can eliminate some of the variables that you don't need. Once you know the type of cone you're dealing with, for instance, your volume can turn into something which only involves R or only involves H instead of both. Back to the question. We have dA by dt equals negative K. We have the area as 4 pi r squared. It's the surface area of the sphere. So we can find dA by dr, the rate at which that area changes with the radius change, which is 8 pi r. We do a similar thing for volume. If volume is 4/3 pi r cubed, then the rate at which the volume changes is 4 pi r squared. It's not a coincidence, incidentally, that this looks the same as this. The rate at which the volume changes for a small change in the radius, how much does the volume change? The surface area is effectively the answer here. What that means is, for a very, very small change in radius, the corresponding very, very small change in volume is essentially the same as the current surface area of the sphere. Another way of saying this would be, if you want to build a sphere, you can do it using infinitely many, infinitely thin spherical shells. The area of the spherical shell is effectively what you add on to the outside of a sphere to increase its volume by an infinitely tiny amount. And that sort of idea works also with circles, pi r squared becoming 2 pi r, because a circle can be thought of as an infinite number of infinitely thin one-dimensional rings that go around, basically. Add up a bunch of circumferences for all the different radii, and you will have the area of a circle. Next, we build our chain. It's very easy to get confused with these, but if you write out every variable you're dealing with and you make sense of which ones you can link to what, it doesn't have to be that horrible. We've got dv by dt because that's what we've been asked to find. We're going to generate it by using dv by dr because the r we know we can cancel with the r by dA. Finally, we'll be able to connect the dA using dA by dt, and dA by dt is something we were given in the question. So let's do it. dv by dr is what we had calculated previously, 4 pi r squared. The a by dr we already worked out to be 8 pi r, but we want dr by dA, so we flip it over. The last bit was given in the question, negative k. The overall result looks relatively simple, minus a half kr. Well, the question asked us to show that the volume decreases in proportion to the radius. So this expression we've got here basically does that. K we know is a constant. We introduced it as the constant of proportionality when we were first told about the constant rate at which the area decreases. So multiplying by a half k is just multiplying by a constant. The fact that it's negative just reinforces the idea that the volume is decreasing, but the proportionality is there because it's a constant, half k, multiplied by the radius. The next thing to do is to find an expression for dv by dt, given the additional information they told us. Air is lost at a rate of 30 centimeters cubed per second when the radius is 5. That means dv by dt equals 30 when the radius equals 5. This was the bit that we wrote down earlier over here. dv by dt is 30 when r equals 5. Worth coming back to that. If you get bogged down in the middle of a question, if you've already carefully looked at and written down everything that you need in a useful notation, then it makes life a lot easier later on down the line. So this last bit is replacing r, the radius, with 5, and then replacing dv by dt with minus 30. We rearrange, we solve, we find k, and we go back and we substitute that value for k back in. We get dv by dt is not just minus a half kr, but it's minus a half of 12r. In other words, minus 6r. That is the expression for dv by dt. The rate at which the volume changes will be greatest when the radius is the greatest, and it's going to get smaller and smaller as the radius decreases. When you meet a differential equation out in the wild, it probably won't be in the form of a differential equation. Chances are you'll have to tease out information about how the variables are connected, what the rates are doing, and what's changing with respect to what. And that is a really useful skill. It's something that you get to practice a little bit in some of these questions. But writing your own differential equation, in other words, an equation that involves derivative terms like dy by dx, etc., from a description is a really important thing to be able to do. We're going to go through a few examples together here. I'll talk about the language and the way that you can interpret the statements. First one, the gradient of a curve is equal to the product of the x and y coordinates. For each of these, if you want to have a pause of the video and try to write down what you think, having a go at it, even if what you get is a bit garbled or doesn't quite make sense, will be more useful, because then my answer will solve a problem that you've grappled with instead of just giving you some information that you've not yet engaged with. So for this one, it's a little simpler than the ones that are going to follow, to be honest. The gradient of a curve. Well, we already know that if we're talking about the gradient of a curve, we should be thinking in terms of dy by dx. And then when it talks about the product of the x and y coordinates, well, that's also something we can write down. We've got notation for that. We can just put x times y. For example number 2, we're going to think about the population of yeast. And the clue in here that it's a derivative is that it's increasing at a certain rate. But then it says it's proportional to something. We've got a proportionality idea that we need to take into account. And what it's proportional to is the size of the population. So that population which is increasing at a rate proportional to the size of that population. This is a very common sort of thing that happens with population dynamics. If you've got a very large population, then it's likely to grow by a large number of individuals in any given time period. If you've got 20 rabbits, then you wait a year, you might have 30 rabbits. If you've already got 200 rabbits, waiting a year will probably end you up with 300 rabbits, as long as there's no other selection pressures involved. It's not that rabbits are friskier when in larger groups, it's more like the rate at which a rabbit population grows, or a yeast population for that matter, is a proportional rate. If you've got a 50% chance of producing an offspring, then so does everyone else around you, perhaps in a population of yeast. Then if you've got lots and lots of yeasts busy trying to produce offspring and 50% of them succeed, the more yeast you've got, the greater the number of offspring you get. So that's why we describe population growth as a percentage, because it doesn't make sense to talk about the total number, because that will change drastically as the number of people in the population changes. A third example is the cooling problem. If you have a cup of coffee that is very hot compared to the surroundings, the ambient temperature of the room, then presumably when you put it down and you wait a bit, the temperature of the coffee will go down. But if it's got a large gap between the temperature of the coffee and the surrounding temperature of the room, it's going to lose thermal energy more quickly. There's what we call a temperature gradient between the hot coffee and the colder surroundings. So while there's a large temperature gradient, it's like having a steep downhill slope, and the thermal energy will be lost from the coffee significantly more quickly while the temperature gap is large, and slower as the temperature gap decreases. The clue that this is a differential equations question is that it talks about the rate at which something happens. That word is a very common one. It's going to come up a lot. It's in the title of the section and everything. The temperature cools at a rate proportional to something. So it's the rate at which the temperature changes. We know it's going to be a d temperature by d time type situation. By the way, when we're dealing with temperature, we often use the variable theta by convention, sometimes capital T, but it can get confused with little t for time or capital T for time period if you're dealing in some situations. So theta is often used to represent the temperature of something, typically in Kelvin or centigrade. I'm not quite sure why. Maybe it's because it's measured in degrees, like an angle might be. But if you're trying to construct the rate at which temperature changes, you could use d theta by dt. There's a couple other things in here. It's got this proportionality thing again, so there'll be some constant of proportionality you need to incorporate. But then the thing it's proportional to is not just, like in the previous question, the size of the population or proportional to the temperature. It's proportional to the difference in temperature between the drink and its surroundings. So we're looking for proportionality according to some other expression that you need to write. Fourth example, a bathtub is simultaneously being filled at a certain rate and also being emptied at a certain rate. You can imagine, depending on the size of those rates, this tub is either increasing in volume or decreasing in volume. But the thing we're interested in here is the rate at which that volume changes. So we see that word again. The bathtub is filled with water at a certain rate, and it loses water at a certain rate. So it's the amount of water we're dealing with, which is the volume, and the rate at which it increases, well, that's just 5 litres per minute. So if that was the only thing going on, you just have dV by dt equals 5. But you've also got a decrease, and you've got to think about how we can incorporate the proportionality into that one as well. One final example as a bonus. If you are in free fall, if you jump out of an aeroplane, then there will be various forces acting on you. We can simplify the situation significantly without losing too much of what's important about what goes on by saying your weight is pulling you down and the drag force of air resistance is resisting that. If you incorporate those two things, the clue here that we're dealing with derivatives is that we're talking about a mechanics situation, and we refer to velocity. Now, the mechanics situation, the free fall experience, the fact that we're talking about a force, that implies something related to acceleration. And in fact, the key link here is between the force that's being described and the velocity. Free fall implies there's a force of gravity. Drag force implies there's a force of air resistance. And then velocity reminds us that actually velocity and acceleration are both derivative terms. They're the rate at which something changes. So you might want to have a play around with that, see if you can construct something that makes sense there. All right, we're going to go through each one now in detail. So if you want to pause and try some more for yourselves before we do. Pause now. Question 1. The gradient of the curve is dy by dx. The product of x and y is xy. So our differential equation is quite simply dy by dx equals xy. For the second one, the population of yeast increasing at a rate proportional to the size of the population. The rate at which the population increases is described as dp by dt. And because it's increasing in proportion to the size of the population, which we've already labeled p, we have dp by dt equals kp. This is the classic exponential growth, as we'll see in a minute. I'll put some graphs up just out of interest. But what you're expected to do within this chapter is not solve these yet, but construct them. So read the information and find a way of writing them as differential equations. For example, number 3. The rate at which the temperature changes is negative for a start, because the temperature is cooling. It is proportional to something, which is why we get a K in there. That's the proportionality constant. And finally, the thing that it's proportional to is the difference in temperature between the coffee and its surroundings. I'm treating theta naught as the temperature of the surroundings. That might be 18 degrees, 20 degrees, something like that. And the coffee itself is going to be hotter than that, unless you're drinking an iced coffee. We're talking about coffee that's cooling down, so we're talking maybe 70 degrees, 80 degrees, and the temperature gap will be 80 minus 20, so you've got a 60 degree gap multiplied by some constant, which we're assuming is positive. K is going to be a positive constant there. Then we put a minus in front to show that it's cooling down. And you can see that if your coffee is 60 degrees hotter than its surroundings, it should be cooling down at a rate twice as great as if it was only 30 degrees hotter than its surroundings. There's a good Matt Parker video on this, whether or not if you're interrupted while making tea, you should pour the milk in and then go and answer the door, or answer the door and then pour the milk in. He does it with a whole experiment and then describes why one method works better than another using this cooling equation. Example number 4. Your bathtub is being filled at a constant rate and emptied at a rate proportional to the volume. For this, we have two components. We can combine rates just by adding them. You've done this intuitively with proportionality questions at GCSE in the past as well. If you've got a swimming pool being fed by two different hoses and one puts in 10 litres a minute, the other puts in 15 litres a minute, then you know that you're getting 25 litres a minute in that swimming pool. We can add these rates together in the same way. So the total volume change in the bathtub will be a combination of the 5 litres that are being inputted every minute and the K times V litres that are being lost, because water is being lost through the plug hole at a rate proportional to V, the volume. That's a minus because it's being lost, and the kV is because it's a rate proportional to the volume, not necessarily equal to the volume. So we don't know the value of K. If K is very small, like 0.1 or something, then presumably the bathtub could be quite happily filling up for a while. But you might find that at some point, if this is the situation, if the water runs out faster and faster, the greater the volume, it makes sense that there would be a volume, possibly beyond the size of the bathtub, depending on the situation, but there could be a volume at which dV by dt is 0, in which case, no matter how long you leave it running for, it's not going to get beyond a certain volume, because you've reached that point where the water is running out of the plug hole as fast as it's pouring into the bath. If you artificially increased it beyond that point, it would be like forcing somebody to move faster than their terminal velocity while they were in free fall. And instead of gradually increasing towards their terminal velocity at that point, they would decrease towards their terminal velocity. That's what happens when you pull a parachute. Your terminal velocity of you with a parachute is a lot lower than what you're currently doing, so your speed decreases. Which brings us on to the bonus example. If you're in free fall, we need to consider the forces acting on you. So the way we construct this differential equation, and this is a little beyond what you'd be expected to do for A-level maths, so don't panic too much about it, but it's an interesting link between differential equations and mechanics, which you'll explore further next year if you do further maths. The way we connect these is by thinking about the forces, but we consider the forces in terms of mass times acceleration. So if we look at the mass of the body that's in free fall multiplied by the acceleration, which we can write as dv by dt, the rate at which the velocity changes, then we can have the right-hand side of the equation being all of the forces that add together. So the left-hand side is F equals ma, basically. The force, the total resultant force, is equal to mass times acceleration, but the total resultant force is also equal to the weight pulling down and the drag force pulling the opposite direction. I'm sort of treating down as positive in some sense here. The downward resultant force is equal to the downward force of weight minus the backward force of drag, which is proportional to the square of the velocity. If you'd done this using the fact that velocity is itself a rate of change, then you might have got an even crazier looking equation. That is the x by dt squared, the square of the velocity. And on the left, d2x by dt squared, that's the rate of change of the rate of change of the displacement. That's equivalent to acceleration again. We're going to do one final example. This one is a conical container, so a cone shape filled with water at a constant rate of 10 liters per minute. Given that the angle of the slanting length to the vertical is 45 degrees, find the rate at which the area of the circular surface is increasing when the radius reaches 80 centimeters in centimeters squared per minute. There's a lot to unpack in a question like this. It can be very daunting, so I'd recommend you try reading it through to yourself a couple of times. You take your time. You try to make sense of each line as you go through, but don't get too bogged down in the details the first time you read through. Try to get a feel for the question, get a sense of what the overall situation is. We're talking about a cone. Imagine a massive ice cream cone type thing. It's got a pointy base and it's wide open at the top. And as you pour water in, it's going to have a circular surface. The top surface of the water is going to form a circle at the very top. That's the exposed part. That's what we're interested in investigating. So here's a picture that might help a little bit. Also, a diagram will help you make sense of the 45 degrees condition. There's a question in the book where the angle is a bit different to this. You've got to do a little bit more clever stuff with trigonometry. I've made my life a bit easier here by making it 45 degrees. If the slanting length is 45 degrees away from vertical, then the height that the cone of water forms relative to the radius of the cone of water, well, those two things are going to be the same because it's a 45-degree triangle. So let's start with defining our terms as we've done before. V can be the volume of water, T can be the time elapsed. The volume's in cubic centimeters here because it talks about the radius in centimeters over here, and it talks about the rate of change of the area in centimeters squared. So although the volume rate is given in liters per minute, I'm going to want to convert it into cubic centimeters so that I can easily incorporate the 80 centimeters and the centimeters squared per minute. Where the area, I'm going to call it capital A, and then R and H will be the radius and the height of the cone of water. It's worth mentioning at this point, we don't care about the size of the conical container, apart from the fact that we're probably assuming it's big enough to contain the water for as long as we want to do calculations. What we're interested in is the changing shape of the cone of water that's inside it. That cone will have a height which is constantly increasing as we pour water in, and a radius which is also constantly increasing. That's the base radius of the circle at the base of the inverted cone. Next, we're going to need some formulae. The volume of a cone is equal to a third of the volume of the cylinder that it would sit inside. So a third pi r squared h. And because of that 45-degree angle, like we've said, the height and the radius are going to be the same. If you've got more awkward angles, or if you know some other information, remember you can do Pythagoras with the slanting length of the cone, and you can do right angle trigonometry with h, r, and l, the slant length. Next, we can use the fact that the height and the radius are the same to give us an expression for the volume that only involves one variable. We've managed to write the whole thing in terms of the radius. The radius seems like a sensible thing to write it in terms of, because the area can also be written in terms of the radius. We've got the area as pi r squared, that's the area of that circular surface of the water, and we've got a volume of a third pi r cubed now. That's pi r squared times r, because r is h. Now we have dv by dt equals 10,000. You'll notice there, that's the 10,000. This is the bit that I nearly made a mistake on before I decided to write down explicitly what v represented when I was creating this. We're talking 10 litres per minute, which means 10,000 cubic centimetres per minute. And we need dA by dt when r equals 80. That's what the question is asking us for. So in that line, I've kind of summarized what we know from the question and what we need to produce. Now we set up the chain. We are asked to find dA by dt, and what we already have is dV by dt. So what remains but to find a link between A and V? And in this case, that's going to come from the shape formulae. We can connect the area of the circular surface of the water with the volume of the cone by linking them both to the radius. So if we can get dA by dr and dV by dr, we can flip one of those over, multiply them together and cancel out the radius, get a direct connection between the rates of change of the area of that surface and the volume of the water. Then we just combine it with dV by dt, and we have a link between the rate of change of the area. We have a link between the area itself and time, so we can get dA by dt. So we've got a bit of work to do. We need to find dA by dr and dr by dV, but we have here dA by dr equals 2 pi r. That's just using the fact that the area is pi r squared. And then we can get dV by dr. That's the rate at which the volume changes. You might be interested again here to notice that the rate at which the volume changes is equal to the circular surface. But if you think about it from an adding tiny slivers of something to build up a solid shape perspective, a cone is built from an infinite number of infinitely thin circular slices. I add another surface area to the top of the cone and I've increased the volume by an infinitely tiny amount. That's the general intuition behind this. It's the beauty of calculus. It's also what makes it so crazy confusing to get your head around in many cases. Now we've got those things, we can incorporate them. So dA by dr, dr by dV, and dV by dt all go together. Remember, for dr by dV, what we found was dV by dr. So we're going to need to flip it over, and that's where we get the 1 over pi r squared from. Put them all together, including the 10,000, and we get 20,000 over r. We were asked to find the rate at which the area of the circular surface is increasing when the radius reaches 80 centimeters. And so it's encouraging to us that we've ended up with something that involves r. The radius is 80. That was part of the connections we made in the first place. If it wasn't, we might need to do a bit more jumping through hoops to convert r into whatever we've got. But if the radius is 80, we can just substitute 80 in there instead of r. That's where your final answer of 250 centimeters squared per minute comes from. That is the rate at which that surface is increasing in area. Finally, exercise 9J is now all suitable. You can try any and all of those questions. I particularly recommend the later ones that involve lots of words, but if you're trying to get to grips with this idea of building a chain, there's some very good questions at the very beginning that give you a lot of the pieces you need to build the chain without complicating things by putting things in long-winded descriptions all in words. The notation is there to help you so you can build up to it gradually. The final thing I want to do is just a bit of a quick bonus. We looked at some examples of differential equations you can write. When you get to the integration chapter, we will talk about how you can solve differential equations. To solve a differential equation, if the differential equation is in the nice straightforward form that you've seen before, if I say dy by dx equals 3x squared plus 7, then you can find y by integrating, by doing the antiderivative, as it's sometimes called, the reverse of differentiation, you can do integration. And that is a perfectly good way to solve differential equations that are of that form. But what we will often be looking at is differential equations that are a little messier than that. They're differential equations where perhaps it's not just dy by dx in terms of x, but it might be a combination of dy by dx and y, potentially other things as well. In some cases, even second order differential equations that involve the second derivative. We'll get onto those if you do further maths. But in chapter 12 of the year 2 course, you will deal with the differential equations that we saw in the first 4 examples on the previous slide. Here's one of them. This was the curve whose gradient is equal to the product of the x and y coordinates. If you solve this, you get an entire family of solutions. Just like when you integrate in general, you'll get a plus c involved. Well, you'll get a plus c involved here as well, but depending on how the x's and y's rearrange when you get y in terms of x, you might end up with the plus c having been incorporated in some other strange way. In this case, it's a vertical stretch scale factor. So you can take that curve that's been drawn there and stretch it by any scale factor vertically, and you'll generate another graph which is equally good at solving that differential equation. There's an entire family of functions which satisfy that differential equation, and you pick any point on that curve and multiply the x and y coordinates, and the result will be the gradient of that curve. Here's another one. This one was the population of yeast. This is a classic exponential growth graph. And in this case, because we had a proportionality, but we didn't know exactly what the proportionality constant was, we've still got that unknown constant in our final equation, as well as the constant that appears due to the constant of integration, which is the scale factor at the beginning. If we had some additional information, then we could find not only k, but a and k in this case. If I said to you, for instance, that the population of yeast started out with 1,000 individuals, then a would be 1,000, because 1,000 times e to the k times 0 is 1,000. And if you had one other piece of information, like after 1 hour there were 10,000, then you could substitute those in and solve to find the missing value of k. This one's the cooling equation. If you solve this one, we get theta equals theta naught, the ambient temperature of the surroundings, plus a e to the minus kt. So the rate of cooling depends on that constant of proportionality k, but it is an exponential rate of cooling that we're dealing with. The difference is, by messing with the value of a, we can change essentially the initial temperature of the coffee. And by messing with the value of theta naught, we can change the temperature which the coffee is cooling down towards. So when t equals 0, we get theta naught plus a. So if you've got an 80-degree cup of coffee, then you're going to want a to be 60 and theta naught perhaps to be 20. And then when t equals 0, the coffee is at 80 degrees. And as time goes by, the temperature will exponentially decay, but not towards 0, but towards 20 degrees, the ambient temperature. Coffee is not going to get cooler than the room surrounding it. And the graph below is actually very similar to the graph above. It's also got elements of an exponential decay. The only difference is this one is approaching a positive value from below rather than from above. This was the free fall situation. No, this was the filling the bathtub. So the rate at which the bathtub increases, there's a maximum rate in this particular case. If t is 0, then we have 5 minus a times 1 all over k. But as t increases, the a term is going to, so the a times e to the minus kt becomes smaller and smaller. That becomes less significant, and v gets closer and closer to a value of 5 over k. So it approaches but never quite reaches a particular value. In this case, someone should put their plug in that bath because it's not going to get any higher than 2.5 litres, it looks like. You can mess with the values of A and of K, and if you know already some information about how quickly the thing is emptying out, you can incorporate those. This graph represents the volume as time goes by. And it kind of makes sense that if the plug hole is only losing you water at a rate proportional to the volume, that when the volume is low, the rate of increase will be high, but the greater the volume gets, the less the volume increases. So the slower the rate at which the volume increases. And these graphs are also very similar to the kind of graph you get for terminal velocity. If you're looking at how quickly you move as you approach terminal velocity, the forces involved get closer and closer to being balanced. So all of these and more you will investigate and be able to deal with once you've covered the integration sections. We'll be coming back to differential equations again, writing your own when we are able to then solve them, and then interpreting them more. They're very fertile ground for dealing with modeling questions. You'll like them.